So I think today I'm just gonna do something easy, much easier than before. Instead of focusing on heavy proof mathematics courses, I'm just gonna focus on some general computational problems and some tips on how to do like the upper quartile or the 25th problems of AMC, which is a global which is a an international mathematical competition for introductory for high schoolers or anyone who's interested. There's like four ranges of topics, so it's AMC 10A, AMC 10B, AMC 10 12A, and AMC 12B. Each of them are actually slightly more difficult, but I think difficult wise concept wise because it covers much more in depth. Then I'm gonna walk through some problems, approximately 10 problems, and maybe you can go to AOP's art of problem solving and then do the problems yourself, since they're not really that hard. And I think the first 10 problems are solvable really easy, and then the 24th, 25th can be challenging for some people, but not for me. So yeah, let's just start then. Uh, so first of all, I'm just gonna uh, just walk through some problems. Okay, first problem. It's from the AMC 12B 2024. The Fibonacci sequence are defined by f1 is equal to 1, f2 is equal to 2, 1, and fn is equal to fn minus 1, fn minus 2 for n equal to 1. What is f2 divided by f1 divided by f4 divided by f4 f2? So I think it's pretty easy actually. So there's a couple of approaches. Let's just do the first one. So the first approach is let's just compute all of this stuff. So f2, which is 1, divided by 1 is just 1. So now f4 divided by f4 divided by f2, which is just 1, 2, 2, 2, 3, which is just 3. And then f6, which is just 3 plus 2, 5. 5 plus that's 8. 8 divided by 3, f3, which is what? Which is 2. Which is 4. Now for f8, we can actually do the simpler version. Now for f8, we know that f6 is 4, then 7, 11. 11 divided by... so no, it's not 11, right? So I think it's gonna be 7. Yeah, it's gonna be 7 since it's 14 divided by this, and the pattern continues. A key observation here is that it's actually a different type of series. It's called I think Lorenz series, and it focuses on L1 is equal to the Fibonacci sequence, but the first sequence, F1, L1, and L2 is actually 1, 3. So this is really key observation. Then this is just 11, 18. 1, 3, 4, 7, 11, 18, and this is just 10 times. 18, 29, 47, 47 plus 29, which is just 56. And the last one is just 66, which is 34, 113. And putting in the sums is just 319. So that's our correct answer. That's our right answer. Now, so this is the first method. There are actually several methods. Let's do the second one. We can prove by induction that, let's say A is just, okay, it's just root 5 plus 1 divided by 2. And B is just conjugate of A. Just conjugate of A. Now, there's a useful notation here. We can use 1 root 5 divided by root 5 f of n of a plus b an plus bn is equal to fn. I think it's minus, yeah. Minus divided by fn. So using this notation, we actually prove that this is for general case 2n, and it's just an plus, since this cancels out, so it's just an minus bn 10 times. So yeah, it's actually really interesting to know. So yeah, I guess that much covers it. So this is you can actually use other problems. You can just directly compute it, but it's a long computation, and like looking at the style, it actually takes a lot of time. So now let's go to the second problem. Okay, now I think I'm gonna do an easier one, so that it's gonna be okay. This is a pretty easy one. So a complex number u is a plus bi and v is c plus di. Define a binary operation x such that uv is equal to ac plus bdi. Okay, we just multiply. Suppose z is a complex number such that zz is equal to what is z? What is the natural log of z? So interesting observations now here. So we're giving those complex numbers, and we know that the binary operation here is acts on this. So here what we actually essentially do is, if z is a set of complex numbers, then z squared should be its first digit, right? And z second should be its 40th digit. So ia. So in some sense, I would probably say it's z can be in the form of 0 in some sort, I think, because transcripting this z squared is just some binary number, right? Okay. So we just multiply coefficients here. So now we can propose the function here and probably just compute this here. Just oh, what was that? Wait. Yeah. So you can just usually do this. So this is left as an exercise for the reader. I think if you actually do the z of complex numbers as z, you can actually use 2 notation. If okay, so let's just substitute, right? So what is 2 here? So 2 z is just, we can multiply 4, which is vividly correct. 4 plus bdi I times 0 times 0, which is 40, which is not in this case. And same for here. So you can just substitute it here, or you can actually solve it mutually, but I guess sometimes it's actually easier to do this since it requires lots of substitution here, especially with those complex numbers, since the z can be defined as z plus some number I in this case. So I can be, since it's a complex number, then it can be I squared. One of them can be I squared. So b can be I squared, and but this is in a set of complex number. Let's say z is in a set of I some constant I. Then if you know that the first term is I, then the second term might be something like b squared I minus 1 times I squared minus I. So that pretty much covers it, yeah. Now, I guess let's just do an easier problem here, and then we're gonna go towards like the hardest ones here, I guess. Okay. So this is solved. I'm just gonna move it here. So now, okay. So this is from the AMC 12B 2023, and what it tells us is, let's just go. Okay. Suppose a, b are positive integers such that a divided by 14 plus b divided by 15 is equal to c 210. Notice that okay, let me just so notice that this times this 14 times 15 is actually equal to 210. So that's an interesting observation here. Which of the following statements are necessarily true? So meaning that there's a proposition for this particular instance that is actually true. So let's say if GCD A is equal to 1, so this is irreducible, and B is also irreducible, or both of them are irreducible. Then we know that GCD of C and 210 is equal to 1. Well, here we can actually, I don't think this is necessarily true. So, but knowing this, we can just compute this, right? So 15A plus 14B is equal to C. So in this case, I don't think the GCD really counts here by Bézet lemma. It can't be really one, but this can apply. Okay. So let's say if GCD is equal to 210, then GCD A14 is equal to 1, and then GCD plus A equals 1. This is, I guess in some sort this can be really true, since by Bézet lemma we can't really say that they're prime factorizable. So it can be two. So the first claim is not true, since they can be, and both of them should be particularly true. For third one. So if they're irreducible, and this is also applies, but this is not really so true. I would say one to only, yeah. So let's just me moving here. What should I do next? I guess let's do the P21 here. So for real numbers x, let p of x is equal to I plus cosine plus I sine x minus cosine 2x minus I sine x plus cosine 3x. Okay, where I is a complex number for how many values of x such that x is in the quartile range of 0 to 2 pi. Does p of 0 exist? So, okay. Here's just an interesting observation. I guess you can actually know the Cartesian coordinates. So p of x is essentially equal to one plus e of x, e of ix. We can prove this. We can actually generally prove this, since minus e 2ix plus e 3ix, and this is all equal to 0. Now, so e of ix, for how many values of x this applies? E of ix times, so here, e of ix times 1 minus e squared plus e cubed is equal to minus 1. It's just a computational problem, right? Okay, so what is, in general, does p of x equal to 3 is 0 equal, okay, minus 1. So here what we actually should do, so, fuck, okay. I guess it didn't really work here. And now for ix, set of complex numbers, you can actually prove, okay. So interesting thing is that we can actually compute this, so, or estimate the answer here, and then find all the values here. I guess this is the only observation you can actually possibly find, since it's actually not that hard to do it. So yeah, I guess so this problem is solved, and I guess this can be left as an exercise for the reader, since it doesn't really require that much logic, and I guess you can do it. Okay, let's do the P17, right? For integers a, m, right, randomly chosen without replacement from the set of integers absolute value not exceeding 10. What is the probability that a polynomial had 3 distinct integer roots? Okay. Three distinct integer. Okay, so a polynomial has three distinct integer roots if and only if it can be factorized in the form of x minus c, x minus c, x plus c, plus x plus c1, let's say c1 plus c2, and that is equal to 0. So this particular polynomial in this case, can actually use the notation here, I guess. Can actually use this. So it's in the form of, let's say, some c value, x. Now here, it should be x squared, right? Now, if this actually is equivalent to x squared, then I think we can actually put this a as a minus 1, and then this is just true for all n. Now, you can actually do the other stuff. Just let's say, okay, you can actually use just substitution, since they're not really not exciting 20, so there are 20 possible solutions here, and just iterating through, you can actually compute this really easily. I guess you can actually put 1 and then just see, because 1, okay, because 2 and 3 necessarily work. They 2 and 3 are 2 and 3 necessarily work here in this particular case. So just check for the end cases. That's it. Now we solved problem 3, problem 9, and let's go to problem, I think, 22. 22. Should I do 22? Which one? Okay, never mind. Let's do the AMC 2022 P20. Okay, so let Px be a polynomial with rational coefficients such that when Px is divided by the polynomial x squared plus x plus 1, the remainder is x plus 2. Okay. When Px is divided by the polynomial x squared plus 1, the remainder is 2x plus 1. The unique polynomial least degree of property. What's the sum of squares of the coefficients of that polynomial? Okay. Interesting problem. I guess. So it's degree 3. Yeah, the polynomial is in degree 3.